Hello everyone. So in this video we are going to cover stellar processes, that is D4 of astrophysics, and this is part that belongs to HL. So first thing that we are going to start with Jeans criteria. So in stellar processes, how a gas cloud converts into a star. So there is a condition given by Jeans. The condition says that if there is a gas cloud of mass m, the gas cloud has a gravitational potential energy, okay, because of the mass being pulled towards the center. So when the gravitational potential energy of gas cloud of mass m exceeds the average kinetic energy of thermal motion of the gas particles, then the gas cloud starts collapsing under its own gravity. So, so this is a condition in which the mass is large enough such that the gravitational potential energy exceeds the average kinetic energy of the random gas molecules because of the random motion. Then this gas cloud will start collapsing under its own gravity, and we can write this condition as a gravitational potential energy is given by G mm by r square, but here there is the same mass, so I will take m square upon r, where r is the radius of gas cloud. It should exceed the average kinetic energy is given by 3 by 2 kT. I will write n, that is the number of gas molecules, kBT, where T is the temperature. Okay, so we can use this formula to prove whether the gas cloud will convert into star or not. So as the gas cloud collapses, the temperature at the core rises, and thus when the temperature are high enough, to produce visible light, then the gas cloud becomes what we call as protostar. Now, protostar is something that it is now hot enough to produce a visible light, but also hot enough to produce like there is some fusion reaction also happening, but it is not stable. Okay, so when a protostar creates enough fusion energy to balance out the lower gravitational pressure, then a producer star becomes a main sequence star. So only when the equilibrium is achieved between the fusion and the gravity pressure, then only our equilibrium is achieved, and that's how a main sequence star is formed from a gas cloud. Now, inside a main sequence star, there is continuously fusion happening. So for stars like our sun, the proton cycle is the main fuel for the sun because it converts hydrogen to helium. The process goes like so. There are two hydrogens. It will convert the isotope of hydrogen, hydrogen to positive and a neutrino. When hydrogen two, that is deuterium, gets react again with another hydrogen, then we get a helium 3, which is an isotope of helium, and when two helium 3s undergoes a fusion, then you will get a helium 4, which is a stable nucleus, and outcome of byproduct of that we have got two more hydrogen nucleus. So basically, we require almost four hydrogen nuclei to produce one helium nuclei. Okay, so you can see that this each helium 3 is formed by three hydrogens, correct? So one helium 3 is formed by three hydrogen, and so we have two helium 3, there will be six hydrogen needed, but there will be also two hydrogen that we will need to subtract. So overall, four hydrogens are needed to produce one helium nucleus, and this is the common process that releases a lot of radiation and energy outward. In a heavier star, more massive star, the gravity and the mass is high enough that it can fuel, and the temperatures are high enough it can fuel heavier items like carbon, nitrogen, and oxygen. This is CNO cycle. So in the CNO cycle, you can see that in one hydrogen is required to convert a carbon 12 to a nitrogen 13. Then nitrogen 13 again is converted into isotope of carbon, that is carbon 13. Carbon 13 being unstable reacts with the hydrogen, converts into neutron, sorry, nitrogen, and then nitrogen again converts into oxygen, then convert back again to nitrogen, and so on. So this cycle process, and you can see that the amount of nitrogen and carbons are used is reserved from the beginning to the end of the cycle. So no carbon or nitrogen is lost in this particular reaction. It is just that there are four hydrogens that are converted into one helium. So there are also four hydrogen nuclei gets converted into a single helium nucleus. Okay, so this is all about CNO cycle, and this is mostly the proton-proton cycle and CNO cycle are the processes of the main sequence star, and they continue. They last for almost billions of years. Okay, multiple billions of years. You will see that this process to be lasting. But when a star ran out of hydrogen, it will convert into a red giant and the process continues. So for a low mass star, the remaining helium that is formed by the fusing of hydrogen, the helium starts fusing with itself and creates a beryllium. Beryllium again then react with helium again to produce a carbon. So for a low mass star, the temperatures and the mass is not high enough to produce or to fuse anything more than carbon 12. So this is the only condition because no master do not have any. So what happens is like the outer layer converts into a planetary nebula. Planetary nebula. Okay. And a white dwarf is formed, which is basically the core of carbon. Okay. So this is all about a low mass star when the mass is less than 8 times the solar masses. And this process is called triple alpha ultra process. Triple alpha process. In this, if there is star massive than 8 solar masses, in this case, heavy nuclei can be fused at the core. And this process starts by converting hydrogen to helium. When helium runs out, then it starts fusing carbon. Then once it forms carbon, it will convert into oxygen. Oxygen straight to neon. Neon converts to magnesium. Magnesium converts to silicon. And then there is a finally iron core. Okay. So this process, the burning of hydrogen lasts for like almost billions of years. Okay. Even the helium lasts for 10 raised to 6 years. For the carbon process, it will last for roughly around 1,000 years. An oxygen process might last for like 200s of years. Okay. Then this neon process might happen for 1 to 2 years. It will fuse. The magnesium will fuse almost a few months, and the silicon to iron fuse into like almost in days. So do rather quickly the process happening because as you fuse more and more heavier nuclei, what happens is like the availability of lighter nuclei to fuse starts getting less. So it runs out quickly. And when the ion is formed, the fusion stops. The fusion stops because iron has iron has highest binding energy for nucleon. Okay. So it can't be fused further, it is energetically not possible. Energetically not possible to fuse hydrogen. Okay. So that's where the process starts, and this star then converts into what we call a supernova. Okay, it will explode. So this is the process that happens beyond the main sequence star, and we can predict the lifetime of the main sequence star. We already know that luminosity is related to mass by 3.5 m raised to 3.5. But here the lifetime of the star, how long it will stay as a main sequence star, it depends directly on the mass of minus 2.5. So I can write this if it is given in terms of solar masses, lifetime of our sun, then this will be m naught m 2.5. Okay. Now, what we have seen is that only till iron the nuclei are formed. So, question is, where does the heavier elements come from in the universe? We have definitely seen heavier elements like uranium, lead, gold, and so many. So, how do they are formed? Like how? Because Earth and I don't have enough high temperature to fuse heavier nuclei. So whatever the nuclei that we have, heavier nuclei that we have, is because of what was in the gas cloud before Earth was formed, and so it has been reminiscent of something. So question was, what is the process that makes the heavier nuclei, heavier elements to be formed? The process is called nucleosynthesis. In this process, the the answer is neutron capture. So what is neutron capture? So when a nuclei absorbs a neutron, it converts, it get converted to a isotope of the nucleus. Okay. Now we have a isotope, and these isotopes are usually stable, unstable, and eventually will decay. Now we don't know when they will decay, but important thing is depending on what situation the isotope was formed, the isotopes usually have two processes, something that we call as one is S process. We also call it as SO process. So in S process, what usually happen in S process is that the isotope gets enough time to decay before absorbing next neutron. Okay. So it will decay. Usually that's usually those decay are beta decay. That's isotopes sometimes undergo beta decay, which increases the atomic number and thus heavier than iron nuclei are formed. Yes. So now this is the S process. So isotope do get enough time to decay before it absorbs, so it continuously undergoes beta decay where the atomic number is increased, thus heavier nuclei are formed. There is another process that is called as R process. That is also short form for rapid process. In this process, the isotope don't get enough time to decay and thus absorbs more and more neutron. Okay, as it absorbs, it becomes heavy. Thus, it becomes a neutron-rich isotope. Okay, thus becomes neutron-rich isotope, and then it undergoes series of decay to produce heavy nuclei. Produce heavy nuclei. Okay, so this is the process, R process in which the process happens. Usually, the S process happens, often happens within the star, while the R process happens because this has a quick process happens within a supernova explosion. Okay, so these are the two processes of nucleosynthesis that we should remember. The last part of this is two types of supernovas. Now there are type 1 is supernova and type 2 is supernova. In type 1, the type 1 is supernova. It is seen when a white dwarf, like this is a white dwarf. So usually this happens in a binary system, binary star system only. So it is seen when a white dwarf attracts matter from a giant companion star, stripping it away. Okay, so we will this is now when the mass of white dwarf exceeds the Chandrasekhar limit. That is roughly around the core can be 2 3 solar masses. So when the white dwarf exceeds the Chandrasekhar limit, the fusion reignites within the core and a bright light is produced for a short span. Okay, so it produces for a short time if the but since it is already a white dwarf which has mostly a carbon at its core, what we see is that there are no hydrogen lines in the spectrum. And the second thing, no hydrogen line in the spectrum. And the second thing, we see that the luminosity falls rapidly. Okay. And since peak luminosity of supernova is same for different. We measure apparent brightness and we calculate the D, which is given by this formula. Okay. So when you substitute luminosity and apparent brightness, you will get the distance. That's why type 1 supernova are used as standard candles. Those just determine the longer distances. Now, in supernova, normal type 2 supernova, it is seen when a red super giant star explodes. Okay. So when the red supergiant star explodes, you will get a type 2 supernova. Now, what's the distinction about this? In the spectrum observed, we can see that the spectrum observed hydrogen lines are C. This is because the red supergiant will have some hydrogen in its outer shell, and that hydrogen can be visible in the spectrum, in the absorption spectrum. Also, one more thing, the luminosity falls less rapidly. Okay, so if I plot a graph of luminosity as versus time, then in that case, I will get it for liquid. This is for type 2 supernova. And this is type 1. So this is all there in D4. I hope you have learned everything. Thank you so much.